flight of airplanes has always been a subject of curiosity in the minds of both the young and old. Many find it hard to imagine how something could lift off from the ground and sustain flight for upwards of 20 hours at a time, with thousands of pounds of weight on it. So today we will be observing the physics behind flight. So take your seats, fold up your tray tables, and join this epic journey. Coming up on our discussion of physics of airplanes, we will be discussing a brief history and background behind aviation, as well as an in-depth look into the four fundamentals of flight, including lift, thrust, drag, and weight. On March 23, 1903, Orville and Wilbur Wright flew the first successful aircraft, the Wright Flyer, in Kitty Hawk, North Carolina. It was the first fully controlled glider that successfully sustained flight. Today we see the implementation of the Wright brothers' work as it revolutionized our lives forever. It is used to successfully transport cargo and passengers, as well as for the military. Commercial aviation is a $20 billion industry, and airlines are now able to transport up to 600 passengers, a staggering 8,500 miles in 20 hours without refueling. The Wright brothers were aware, and they took account of the four fundamentals of flight, which are lift, thrust, drag, and weight. Now let's look at our first formula. This formula is F equals ma. In this formula, force is equal to the mass of the aircraft multiplied by its acceleration. F is equal to force, m equals mass, and a equals acceleration. This formula can be used to determine the force that the thrust from the engine has. Thrust is created when the turbine or propeller of the engine pulls air from the front of the engine and shoots it out the back of the engine to create kinetic energy and push the aircraft forward in the air. This force is what allows the aircraft to have a forward momentum. So now let's look at a word problem. If a Boeing 737 with a mass of 3.4 times 10 to the 4th kilograms is traveling eastbound at an acceleration of 160 meters per second squared, what is the force of the aircraft? To put it into perspective, 34,000 kilograms, the equivalent of a small aircraft, is the equivalent of about 6 full-grown male elephants. Now that we know what our formula consists of and what the variables represent, we can now solve this problem using the VFPA model. Now, this stands for variable, formula, problem, and answer to solve this problem. Now simply we will list out the variables, and m is the equivalent of 3.4 times 10 to the 4th kilograms, and a, acceleration, is equal to 160 meters per second squared. Now simply we will find the product of these two by plugging them in, plug and chug, and you multiply them together, and our product comes out to 5,440,000 newtons. This is the equivalent of 5.44 times 10 to the 6th newtons in scientific notation. 1 newton is approximately the same as 0.1 kilogram. So 5,440,000 newtons would be approximately the same as 550,000 kilograms. There is a direct relationship between force and acceleration. As acceleration increases, so does force. This formula can also be used to determine the force of a pendulum. Same principles apply. Now let's put this into action. In this video, a Formula 1 race car will go head-to-head with an Airbus A320, a medium-sized aircraft. Although the winner is obvious, let's watch this. Now the reason the Airbus won is because its engines have more force to offer and in turn has a greater acceleration. Our next formula is L equals 1/2 times rho times CL times V squared. This formula is used to calculate lift. Now let's hear an expert explanation of these variables.
So rho, it's not a P, it's the Greek letter rho. Rho is the density of the air, which is a measure of the number of air molecules in a certain volume. Density of the air varies with altitude and temperature. So as you go higher up, the air is thinner, and so the density is lower. If we want to simplify things, we generally use the standard density, which is 1.2754 kilograms per meters cubed. V here is the speed of the aircraft, or how fast it's traveling. And CL is something called the coefficient of lift. It's a number that gives us some information about the shape of the aircraft's wings. Now, the angle formed here by the horizontal direction of travel and the direction of the aircraft's nose is called the angle of attack.
This formula is used to determine the amount of lift of an aircraft. Now this is a cross-section of an aircraft wing. Without its elongated teardrop shape, lift is not possible. The shape of the airfoil, or wing, is engineered to allow the air traveling over the wing to move faster than the air under the wing. The slower air pressure therefore causes an upward lift. Relatively, the engine barely has to do any work at all. The aircraft continues to fly due to inertia and basically acts as a glider, thanks to lift and Newton's first law of motion. The principle of lift has a direct relationship. As the angle of attack increases, the coefficient of lift increases. However, there is a certain degree, different on every aircraft, where stall occurs. This is because the airflow over and under the wings is interrupted by the wing slowly becoming diagonal and or perpendicular to the ground. This is very dangerous, and it prevents the aircraft from remaining airborne. This is what happened to Asiana Flight 214 in July of 2013, as it was landing in San Francisco. The pilot pitched the aircraft too high, and the aircraft lost airspeed, and eventually the lack of lift resulted in a decrease in altitude, resulting in the crash. Next, let's look at a word problem. An aircraft at standard cruising altitude is ascending at an angle of 15 degrees, at a velocity of 150 meters per second. What is the lift? Again, we will use the VFPA method and we will list out our variables. So our angle of attack, CL, is equivalent of 15 degrees, and our velocity equals 150 meters per second. Now let's look at our formula. L equals 1/2 rho times CL times V squared. And now it's time to plug it in. Now we will be using the standard air density for rho, which is 1.2754 times CL, our angle of attack, which is 15, and our velocity squared, 150 squared. And we end up with 430,447.5, and now we will divide this by 2, and our total comes up to be 215,223.75 kilograms per meter cubed. And we will round this up and put it in scientific notation as 2.15 times 10 to the 5th kilograms per meter cubed. Now let's see a demonstration of a takeoff in Microsoft Flight Simulator. As more thrust is applied, the aircraft speeds up and lift increases as it speeds down the runway and it lifts off.
V1. Rotate. Positive rate of climb. Gear up.
The principles of lift also apply to a curveball in baseball. W equals mg. W means weight, m equals mass, and g is the gravity constant. Gravity is the only constant factor when it comes to flight. There are positive and negative g forces. Positive when the aircraft's nose is pitching up, and negative when it is pitching downwards. There are different factors that can contribute to the mass of the aircraft. These include fuel, passengers, payload, and the aircraft itself. Weight is one of the greatest factors that determine the aerodynamics of an aircraft. A heavy load can decrease the maneuverability of the aircraft, as well as hinder its fuel economy and performance, very similarly to a car. The heavier the load, the more impact it's going to have on how much fuel it burns and how much strain is given on the aircraft control features. To demonstrate this, let's look at the next word problem. Flight 1042 is about to land in Chicago. The aircraft is traveling at an altitude of 1.04 times 10 to the 4th meters and has 2.2 times 10 to the 4th kilograms of fuel on board, as well as 2 times 10 to the 4th kilograms worth of passengers and payload. What is its weight? Time to list the variables. Now first off, g is the acceleration due to gravity, and it is equal to 9.81 meters per second. Now we just have to combine m1 and m2, the weight of the fuel and the passengers and payload. In this problem, m1 equals 2.2 times 10 to the 4th. And m2 equals 2 times 10 to the 4th. And now we just have to combine the m1 and m2. And when we combine that, we get 4.2 times 10 to the 4th. That's w equals. And now we will simply just multiply this by the gravity constant, which is 9.81. And our total comes out to be 412,020. And in scientific notation, this is 4.1202 times 10 to the 5th kilograms. And that is how we calculate weight. Mass and weight have a direct relationship. When mass increases, weight increases, given that the gravity is constant. P1 plus 1/2 rho v squared plus rho times g times h1. P is the pressure, rho is the density, v is the velocity, h is the elevation, and g is the gravitational acceleration. But what does this all mean? Well, now we will be talking about Bernoulli's principle. This correlates with the last of our 4 factors of flight, drag. Drag occurs when the front of the aircraft is pushing on the air in front of it. This puts a force on the aircraft which limits its velocity. Another word for this is resistance. Bernoulli's principle is one of the key features of flight. As the velocity of a fluid increases, the pressure exerted by that fluid decreases. A slow-moving fluid exerts more pressure than a fast-moving fluid. Pressure and velocity in this equation are inversely proportional. As pressure is high, velocity is low, and vice versa. Now let's hear an expert explanation to how this relates to aircraft.
Lower pressure is caused by the increased speed of air over the wing, and the area of pressure under the wing is higher, the wing is pushed upwards, thus making the plane stay in the air, stay afloat. You see, air moves faster over the upper surface, which causes the air pressure to decrease. The lower air pressure over the top of the wing gives it lift, but some air is directed beneath the wing, which the lift must exceed the weight if the aircraft is to fly.
Now let's look at an experiment of how this can be used by keeping a ping pong ball in the air with just a blow dryer and a soda bottle top. It stays afloat because it is in an area of low pressure and the velocity is forced to increase, cancelling out the forces of gravity. What is the lift in newtons on a wing of an aircraft 6.1 times 10 to the third meters in the air if the aircraft is climbing at 140 meters per second? In this problem we have three constants. G is 9.81 meters per second and rho is 1.2754 kilograms per meters cubed, and P1 is equal to 101.325 kilopascals, which is the standard air pressure at 0 degrees Celsius in the air. Now we just plug in the values for h and v, which are height and velocity. H equals 6.1 times 10 to the third power. Velocity equals 140 meters per second. Now we have our variables, we have our formula. All we have to do now is the problem itself, plug and chug. Now first we add the P1 value, which is 101.325, and add that to 1/2 of rho, 1.2754 times 140 squared, and add that to rho again, 1.2754 times gravity, and multiply that with 6.1 times 10 to the third. There were three parts that we had to add up, and when we plug and chug all this in, our answer 88,921.46 newtons, and that would be 8.8921 times 10 to the fourth newtons. And this right here is the lift of our aircraft in newtons. All in all, we went through the background behind aviation and used four formulas to describe the physics behind flight, which include F equals ma, L equals 1/2 rho CLV squared, W equals mg, and P1 plus 1/2 rho v squared plus PGH1. This helps us go further in depth into the four fundamentals of flight: lift, thrust, drag, and weight. Thanks for watching.